All right, so we were talking about how to reduce exposure and again time distance shielding, and I showed you this before the power went out. So this woman in a hospital has a radioactive implant inside her body, so there's the risk of external exposure. So what the medical person does is he stands behind this shield. This is probably leaded, who knows what, lead or something like that. This is really, really thick leaded glass probably. So a shielding. If you work in a lab and you're using, let's say, a beta emitter, you'd have the beta emitter behind this. Now, if you're making cobalt-60 sources, which are incredibly dangerous because they emit gammas, so then everything is remote. So you're in this, well, you're outside the cell, because that's very, very dangerous. All right, last little topic, particle physics. There's a little section of particle physics at the end of the chapter. So when I was in high school, we were taught that molecules are made of atoms, atoms are made of protons and neutrons and electrons, and that was it. Well, since then, physicists have discovered that protons and neutrons are made of smaller particles called quarks. Oh, by the way, I've showed that before. That's a particle accelerator where it used to work. All right, so quarks. So this is the modern atom model. Electrons are in constant motion around the nucleus. Protons and neutrons jiggle within the nucleus, and quarks jiggle within the protons and the neutrons. All right, so there's 6 kinds of quarks. They have some kind of strange names. So the first generation, these were the first that were discovered, the up and the down. After that, the charm and the strange. After that, the top and the bottom. And they come in 3 varieties. We call them 3 different colors. Okay, so, and these all have electric charge 2/3 of the charge of the electron. And these 3 have the electric charge of 1/3 times the charge of an electron. So this is the first time that we've ever discovered anything that had a fractional charge. So a proton is an up and a down. So see this here? Up, up, down, that's a proton. Up, down, down is a neutron. So let's see how that works out. So a proton has a charge +1, right? So a proton is an up, up, down. So a up has a charge 2/3, but there's 2 of them, so there's 2/3 plus 2/3. And a down, it's -1/3. So -1/3, so 4/3 minus 1/3 is 1, so it works. And then the neutron is a up, down, down. So up is 2/3. Downs are -1/3, so 2/3 minus 1/3, minus 2/3 is 0. So there you go. All right. Now, these quarks, they're confined to within the proton and within the neutron. So they're confined to approximately, about 10 to the -15 meters. Now, you remember the Heisenberg uncertainty principle. If a subatomic particle or a particle is confined to an incredibly small, region, that means there's going to be a large uncertainty in the velocity. So if you use this in the Heisenberg uncertainty principle, just guess. What do you think the uncertainty in the velocity is going to be? Well, it's going to approach the speed of light. All right, so think about it. The uncertainty in the velocity of these quarks approaches the speed of light. So that means to approach this correctly, you need special relativity. Also, the quarks are incredibly small, so to handle that properly, you really need quantum mechanics. So really, if you want to study nuclear physics properly, you have to learn relativistic quantum mechanics, which is what they usually teach in graduate school. All right. Okay, so there you go. And I told you this before when we did relativity. In order to discover the top quark, the protons and antiprotons had to be moving really, 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 really fast, because a lot of their kinetic energy was converted into matter. You remember that the mass of the top is 182 times the mass of the proton. So that's an example, again, where energy became mass. Okay. All right, so let's review. Nuclear physics. We talked about the structure and composition of the nucleus. Understand the forces that hold the nucleus together, the nuclear strong force, and under what circumstances it might break apart. Distinguish between different types of radioactive decays, alpha, beta, and gamma, and compute the daughter nucleus for these decays. Use the concept of half-life to determine the age of a radioactive sample, or the Earth. Develop an understanding of some applications of nuclear physics, an appreciation of some of the principles of particle physics. Woohoo! All right, so remember the nucleus made up of protons and neutrons, and here's the important thing, that mass number is the number of protons plus the number of neutrons. Super small, 10 to the minus 15 meters. Tightly bound. I just showed you that. The concept of isotopes. Isotopes, there's all different types of carbon. They all have the same number of protons because that's what makes a carbon, but they have different numbers of neutrons. And so they have very different nuclear properties. This is the line, so this is the number of neutrons, number of protons. This is the line N equals Z. You can see that not a whole lot of isotopes are along this line, except for down here. They go up here, which is called the line of stability, and these have many more neutrons than protons, and the reason, as we learned, is because neutrons interact with that nuclear strong force. So you need neutrons to hold that nucleus together. We talked about binding energy, the energy that you need to bust up a nucleus. We worked some examples with that equation. We talked about fission and fusion. Remember, fusion, you combine, just like fusing your back vertebrae. In fission, you break up. This is really important. How come this reaction occurs? Where does this energy come from? Well, it's equals mc squared. The mass of the 4 protons is greater than the mass of the helium, so some of that mass was converted to energy, just like Einstein predicted. Yeah, we talked about that. Nuclear strong force, it's an attractive force. Neutrons attract neutrons, neutrons attract protons, protons attract protons. But again, protons repel each other electrostatically, but the nuclear strong force is much stronger than the electrical repulsive force. Radioactivity, it's spontaneous, releases energy, and it's dangerous. And these are the 3 main types. Okay, beta. What's so great about beta? The proper understanding of beta decay helped people discover the neutrino. So that's important. Okay, all these equations for decay, this is the one that we use most of the time. And it uses half-life. Again, after 1 half-life, half of the radioactive material has decayed. So half remains. But again, what you actually measure with a meter is the activity, or the decay rate, which is this. All right, then we talked about the shell model and how the shell model predicts what's going to beta decay, beta minus and beta plus. And then we talked about large Z, how more neutron states than proton states, and so forth and so on. And radioactive decay, we talked about 2 methods. This is one method. Then we used the worksheet for the other method. And health physics, the energy absorbed is the dose in grays. The dose equivalent includes the RBE, the radioactive biological effectiveness or something like that, right? So dose equivalent, sieverts, dose in grays, but don't forget the units don't work like they do in other things. Sieverts equals dose times a number. Horrible. That's how it is. And then again, time, distance, shielding. If you ever work with radioactive materials, you will know this like the back of your hand. And then, of course, particle physics, quarks make up protons and neutrons. So now, of course, the next question is there anything smaller than a quark? Well, we're looking, but we don't know yet. Thank you very much. That's it.